I'm going to tell you about how mathematics gets into knots. But before we do that, let's talk about how knots get into the life of man. Now, this must go back to the oldest times, although all traces of these, or most traces of these, have been lost. It's even been said that the Stone Age should be called the Age of String, because all those axe heads and so on which we find must in fact have been tied to something. If you didn't get the attachment right, then you must have been in deep trouble. But what's the oldest known knot which we really have evidence for? Here we'll show a slide of something. Now, this rather funny looking thing is in fact the remains of a fishing net. Now, the fishing net, when it was originally found, was in a peat bog in Finland. And the net was 30 meters long, 1.5 meters wide, with a 6 centimeter mesh. It was made of willow bark, and the knot which was used in the net, which you can see a diagram on the left, was the bowline which is still used in fishing nets today. Now, the amazing fact about this knot is that the whole fishing net dates from 7,200 BC. That's 9,000 years ago. And it's quite amazing to think of what kind of culture and social organization could have actually developed such an intricate kind of net and tackle. Let's go on to a later time. Here we have a knot from the door of Tutankhamun's tomb from ancient Egypt. In later times, we have Celtic knots. Here is a picture of the Sutton Hoo buckle from the burial chamber in Britain. We also have an Allegheny cross from Ireland. We have an illustration from the Book of Kells, and also from the Tara brooch, again in the National Museum of Ireland. Just to look at the diagrams of the interlacing on the Celtic crosses, you can see how intricate they are. And in many medieval illustrations, you have very intricate knotted elements like this. Now let's move on to a later period. Here we have some trefoils done by the graphic artist M.C. Escher. And in a more elaborate vein, here we have intricately interlaced snakes, getting thicker and thicker as we go either to the edge or to the center. From current times, we have some amazing sculptures by the sculptor John Robinson. Here we have Bond of Friendship, then Eternity, then Immortality, and this very remarkable sculpture, The Rhythm of Life. But knots, of course, aren't only used in art. They're a very important part of practical affairs. Here we have knots used in mountaineering. And without those knots being accurate, he would be in deep trouble. Here we have knots used in an aerial ropeway. And, of course, far more important right throughout history is knots used in fishing and sailing. So here we have some slides coming from the Ashley Book of Knots. Now, these drawings were made by the American whaler Clifford W. Ashley, who made a compendium of knots giving 4,400 knots from all walks of life. Knots, splinets, slices, and hitches. And I'd like to give you a quotation from the Ashley Book of Knots, which is very appropriate to our story. To me, the simple act of tying a knot is an adventure in unlimited space. A bit of string affords a dimensional latitude that is unique among the entities. For an uncomplicated strand is a palpable object that, for all practical purposes, possesses one dimension only. If we move a single strand out of the plane, interlacing at will, actual objects of beauty result in what is practically two dimensions. And if we choose to direct our strand out of the plane, another dimension is added, which provides an opportunity that is limited only by the scope of our own imagery and the length of a rope maker's coil. What could be more wonderful than that? But there always seems to be another car ahead in every likely parking space. Here is a Mr. Klein, claims to have proved that knots cannot exist in 4 dimensions. That in itself is bad enough. But if someone should come forward to prove that heaven does not exist in 3 dimensions, what hope is there left for the confirmed knot tire? Why cannot knots exist in 4 dimensions? Let's show this on a piece of paper by analogy. Here we have a plane, and suppose he wants to cross the line. So he marches along and comes to a stop. So he hops out into 3 dimensions and carries on over there. Well, now let's look at the same situation with regard to string. Suppose we want to untie a knot and we're allowed to use 4 dimensions. We take our piece of string and we bring one edge past another. So here we come to there. And then we hop out into 4 dimensions and then come back on the other side and move across like that. In this way, we can untie any knot using 4 dimensions. But mathematicians are not content with a simple answer like that. If you can untie any knot in 4 dimensions, then the other question is, what can you tie in 4 dimensions? And the nice answer is you can tie a balloon. So suppose you take a spherical shape like that, then you can tie that in 4 dimensions, and you can untie it in 5 dimensions. Proof of that is rather difficult, and so you can go on to higher dimensional spheres. Right, now how did mathematicians come to study knots? Well, the story goes back to the 19th century when they were interested in atoms. The question was, what were atoms like? And they had to explain several facts that they knew about atoms. First of all, they had to explain the permanency of atoms. They always remain the same. The next more complicated thing was they had to explain the vibrations of atoms, which were shown by the spectral lines which they found in looking at light from, say, the sun. And then they had to show the variety of atoms as shown by the table of elements. So one of the key points was the permanency of atoms. Now, Kelvin was rather impressed by some smoke rings which were made by his Scottish physicist friend P.G. Tate. And what he really was impressed by was the permanency of them. So he then thought, how could you get the variety? You've got the permanency, even with a smoke ring you've got the possibility of vibration. How could you get the variety? So he had an idea that the variety could come from them being knotted and linked. And so he wrote a paper on this for the Royal Society of Edinburgh. This was in 1867. Diagrams and wire models were shown to the Society to illustrate knotted or knitted vortex atoms, the endless variety of which is infinitely more than sufficient to explain the varieties and allotropies of known simple bodies and their mutual affinities. They don't write like that nowadays. Now, this theory turned out to be totally wrong, but it inspired Kelvin to work on the hydrodynamics of vortices, and it inspired his Scottish physicist friend P.G. Tate to work on classifying knots. And for the next 10 years, he worked on making lists of knots to see whether they did correspond to the list of atoms, and it was quickly found that they didn't. Then C.N. Little, a Canadian mathematician, spent more years making lists of knots. So, what's the basic problem of knot theory? Well, you take a piece of string like this, and this is unknotted. And then you tie a knot in it like this, and this gives the simplest of all knots, which is a trefoil. Now, actually, it gets rather boring to hold both ends, so what you do is tie both ends together, like this. So what you're actually dealing with is a loop of string, like this. And now we have a picture of it. That's the simplest of all known knots, the trefoil. Now, what do we mean when we say that the trefoil is knotted? Well, what we mean is that however we pull and push this, then it must still be knotted, and the only way we can unknot it is by cutting the string, or maybe by undo like that and slipping it through like that. But in the normal run of events, you can't actually unknot them. Now, the interesting thing is to make tables of knots. So here we have the beginnings of a table of knots. Each knot is defined by its diagram, such as this one showing overpasses and underpasses, like that. We have names for the first three ones, and the numbers here represent the numbers of crossings. You have 3 crossings, 4 crossings, 5 crossings, so 2 knots with 5 crossings, 3 knots with 6 crossings, knots with 7 crossings, and then we move on to knots with 8 crossings down here. So here we have some more knots with 8 crossings. Then we go on to knots with 9 crossings, and so on, running down the page, down to here. So now here we have some more knots with 9 crossings coming down here. So these diagrams show some of the basic problems of knot theory. How, in fact, do we know that all these knots are distinct? This is really a very basic problem. Also, I must say something more about the way these diagrams are constructed, because these are diagrams of knots with the minimal numbers of crossings. Here is a picture of a trefoil with 4 crossings. So this has got more crossings than are needed, because obviously we can unravel this bit. So what we try and do in the knot diagram tables is actually show a diagram of the knot with the minimal number of crossings, provided we're actually sure that the diagram does have the minimal number of crossings for that particular knot. Right. Our next diagram illustrates one of the basic problems of knot theory. Here we have pictures of 2 10-crossing knots. Are they the same? Well, these were represented as different knots for very many years, and finally Perko in 1974 showed that they actually were the same. The diagrams still do not show every knot. One of the reasons is that each knot has a mirror image. For example, here are 2 trefoils, and this one is the mirror image of that one. Now, in fact, by playing around with these, you can show quite easily, to your own conviction, that these are different knots. But it's really quite another matter to prove that they are different. On the other hand, here are 2 mirror image figure 8s. And it actually turns out that these are the same. To prove this, we work as follows. Here's the same figure 8 turned on its side. Just for emphasis, I've colored this a bit differently. If we rearrange it a bit, it looks like this. Here's the mirror image figure 8. If we rearrange it a bit, it looks like this. But now you can easily see that if you take this one and rotate it, then you get this one. So this is how you turn this figure 8 into that figure 8. So the tables do not list the mirror images of knots, even when the mirror image is a different knot. But once again, we still do not list all the knots. To explain this, we have to introduce a new idea, the arithmetic of knots. Now, this is actually one of the surprising things about mathematics, which is the idea of analogy, which, as I mentioned earlier in connection with dimension, is a very important feature of the way mathematics behaves. Here we are going to develop an analogy between knots and numbers. So how do we do this? Well, we're going to show how to add 2 knots. Here is how we do it. Here we take a trefoil, here we take a figure 8. Pull a little bit out of this, pull a little bit out of this. Join them together like that, and that gives you the sum, which is called k plus L. This has some rather nice properties. For example, if you take the figure 8 and you tie the unknot, nothing to it, then what you get is clearly the same thing. This is represented algebraically by saying k plus 0 is k. That's clearly the same as 0 plus k. There's another nice rule. This is called associativity. It says that if you take a trefoil and a figure 8, and then say this knot, we'll call a pentoil, and you tie one after the other, then it doesn't matter about the way you bracket them. I say again that this is called associativity. All of these correspond to some very well-known facts about numbers. Now there's another very nice rule that you can have. and this is called commutativity. We'll first of all illustrate these by diagrams. Here we take a trefoil and a figure 8. Now we pull the figure 8 through the trefoil through the figure 8 like this, and then it comes out on the other side. So this is represented by the rule k plus L equals L plus k. That rule is called commutativity. Now we're going to illustrate some of these rules using actual pieces of string. So here we have our piece of string. First of all, we tie a knot in it. Now, if we tie the unknot in it, like that, then of course we get the same thing. So that's k plus 0 is 0 plus k. Now suppose we tie a nice big and complicated knot. Let's try and do it like this. Right, now if our unseen helpers can hold the ends. Right, now we're going to illustrate k plus L is L plus k. Here are the two knots. Now we expand this one. If you can pull, Colin, then we see that this one comes nicely through. And there we've got them the other way round. Just to prove there's no tricks, let's go back again. So we expand this one. Right, if you can pull, Chris. And here we come through the other way. So that's our actual proof of the rule k plus L is L plus k. We're now going to push this analogy between knots and numbers a bit further. Here we have again some more pictures of a few knots. But these don't represent all knots. In fact, these represent what we call prime knots. To explain this, let's consider the prime numbers. So here are the first few sets of prime numbers, in fact all prime numbers under 100. What do we actually mean by a prime number? Well, a prime number is one which is a product only of itself and 1. And a crucial factor is that any number other than 1 can be written in essentially one and only one way, as a product of prime numbers. So what do we mean by a prime knot? Well, a prime knot is a knot which can be represented only as a sum of itself and 1. And the amazing fact is the following, that any knot other than 0 can be written in essentially one and only one way, without regard to order, as a sum of prime knots. So here we have our amazing analogy between knots and numbers. So here is our analogy. We have knots correspond to numbers, plus corresponds to times, naught corresponds to 1, prime knot corresponds to prime number, a knot being a sum of its summands corresponds to a number being a product of its factors. Notice that it is not the objects themselves which are similar, but the way they behave which is similar. This is very important in mathematics. I should say this is one of the important things about mathematics and the way it progresses. One of the really exciting things about mathematics is the idea of analogy. And the very idea of that reminds me of. That is the thing we really find exciting in mathematics. And very often tools or methods that we use in one subject can be used in another and get very strange and exciting results. So we are also interested in knowing how many prime knots we have of a given type. Starting with three crossings, we have one with 3 crossings, but we don't distinguish between a knot and its mirror image. One with 4 crossings, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the total number of knots with not more than 13 crossings is 12,965. And it is actually a great problem to decide whether or not these knots really are all distinct and that we have actually got all of them. Now, with any analogy, we're interested not only in when the analogy holds, but in when it breaks down. With numbers, there is a standard way of determining for any number how to represent it as a product of prime numbers. The difficulty with knots is that there is no standard method of learning how to write any knot as a sum of prime knots. And this is quite a difficult problem. There are also some unsolved problems in this area. With any knot, we have the notion of a crossing number. And looking again at our number of prime knots, the number of knots with a given number of prime knots with a given number of crossings. So we can now define C of k for any knot as the minimum number of crossings in all possible diagrams of k. The question is it always true that the crossing number of a sum of two knots is the sum of the crossing numbers? This is an unsolved problem. It can all easily be proved that this number is less than or equal to that, but do we actually know that they are equal? And nobody knows the answer. Right. I'm now going to tell you of another mathematical idea connected with knots, and that's the notion of paths. The motivation of this came from an old branch of science, celestial mechanics, which was the study of the motions of the planet and the stars and the moon and the earth. Now, as you know, these were described in ancient times, and Kepler gave the fundamental laws of planetary motion, which said, for example, that the Earth moved round the Sun in an ellipse with the Sun as its focus. So here's our diagram for that. And Kepler's law for this was one of the basic discoveries of 17th century science. Now, it was Newton who showed that these motions of the planets followed from the inverse square law for gravitation, and in so doing he had to invent the calculus. And this is a very great achievement of science in the 17th century. But the next problem that came out, once you've described the motion of one planet around the Sun, how do you describe the motion of, say, three bodies, like the Earth, the Moon, and the Sun? So this was called the three-body problem. And mathematicians worked on it for very many years without making too much progress. In fact, it was even proved that you cannot find any finite formula, any particular way of describing the motion. Although, of course, it is possible to work out how the motion goes to any prescribed degree of accuracy, and even more so with using computers. So how does one actually go about this problem? Now, Poincaré, at the end of the last century, invented an entirely new way of doing this and of looking at the problem. What he realized was that if you cannot actually describe a particular formula for the motion, then what you're interested in is some kind of qualitative question about how the things go. Suppose we start with three bodies, these three. You kick them off in any direction and you want to describe what actually happens. But if you cannot describe it too precisely, maybe there are some other kind of questions that you want to ask. So let's look for the really interesting questions. These interesting questions are of three types. So here are our qualitative questions. What are the periodic solutions? That is, are there solutions which come back to their initial starting point? Is a solution stable? That means if you perturb the initial starting point at all, does the solution remain more or less the same? And then, is the solution bounded over all time? That is, do the bodies stay reasonably near together over indefinite time, or do they go further and further apart? So this is a good illustration of the maxim that in science it is very often not what is the answer that is the interesting question, but what is the interesting question? What is the question in the first place? Now, Poincaré decided on a qualitative approach to the three-body problem. You have three bodies, each of which is described by three coordinates of position and three coordinates of velocity. So with each body you have 6 coordinates, that gives a total of 18 coordinates. Right, but then the motion is described by some kind of path in this big 18-dimensional space. But once you've kicked off the bodies, then there's an energy equation, because the energy is going to be constant throughout all time. So this restricts the number of dimensions to 17 dimensions. And what you're interested in is in describing the motion of the three bodies by some kind of path in this 17-dimensional space. But what we said before was that you were interested in the qualitative type of the motion. So really what we want to say is when are two motions in the 17-dimensional space actually near to one another? And this introduces the idea of deformability. Now we imagine that our 17-dimensional space is represented by this two-dimensional plane. To show that it's complicated, we have some sort of hole in it. Here we have one kind of path A, another kind of path A dashed. It's very reasonable to say that these two paths are fairly similar, and this path is different from B. So this path we say is deformable into that path, but neither of these paths is deformable into that path. Now this can be illustrated with knots and string. Now we're going to use the idea of paths to study this kind of knot. So here is our knot. How do we study it? Well, what we're actually going to do is study the space around the knot. How do you study the space around a knot, or any space at all? Well, if you go to a strange city, you take a walk around it. So if you want to study the space around this knot, what we do is we take a little walk around the knot. Well, if you're going to take a walk around it, it might be an idea to take a piece of string with us so that we record exactly where we've gone. So we go around here, and so on. So let's consider the idea of starting from our original point and coming back again to our original point. This is the notion of a loop. And then we have the notion of doing another loop. That's called the composite loops. And this we can actually show on a diagram. So here we go on loop A, and then we go on loop B, and that's called the composite loop AB. Now another thing we can do, having done a loop like this, we can do the same thing in reverse direction. And clearly we've got back to where we started. Also, if you go round there and then do nothing, we're clearly in the same position. Now if we stay here and then go round here, then we've clearly done the same loop. And finally we have an associativity rule that if we do this one, and then this one, and then that one, then it doesn't really matter which way we bracket them. So that's an associativity rule. Also, we're not really interested in the loops themselves, but in the idea of the class of the loop. That is, we regard two loops the same if one can be deformed into another. That is, we don't mind how this goes around here. So the class of these loops obeys some rather basic algebraic rules. These are called the rules for a group. We're now talking about the group of paths. First of all, we have the identity rule that A times 1, that means stay where you are, is 1 times A, stay where you are, and then do something equals A. Then we have an associativity rule, A bracket BC, the same as AB bracket C. Finally, we have the inverse rule, that if you go off somewhere and then do the same thing in reverse direction, then that's equal to 1, and similarly the other way around. So these are the basic rules for a group. How does this work with our knot? Well, what we're going to do now is label these particular overpasses in a certain way. And we're going to have a label for going round an overpass in this direction. This is shown in our next diagram. We label the overpasses like that, and we also put an arrow on the knot. So we call this one X and this one Y in that direction. And now we're going to label a path or a loop which goes round the knot like that, around this particular overpass which is labeled X. We're going to label that path also X. Right. So now we have names for the ways of going around particular places in this knot. Actually, there are additional rules to the rules for a group which we mentioned earlier. That's shown in this diagram. Here we imagine a particular crossing. This is labelled x, this is labelled y, and this is labelled z. Suppose first of all we imagine a loop which comes under y. And we can move it over a bit so that it goes like that, or we can move it under it so that it goes like that. So if we imagine going under here and then back up again, under here and then back up again, and then under here back up again, that tells us we're actually going to go x, z, and x to the minus 1 because we're going in the opposite direction. So we have the basic rule, y is x, z, x to the minus 1. Now this also can be represented in our knot. Suppose we take this situation. If we go under here, and under there, and then under there, then that's the same as just going round there. So that's the basic rule. Y is equal to x, z, x to the minus 1. Right, now we're going to do some real algebra. Here we have our diagram for a trefoil, and here we've labelled the overpasses, and we've also got an arrow. And what I said previously was that we have a rule at each crossing. So here we have the one on the left is equal to x times the one on the right times this one again. So that's the rule. Z is x, y, x to the minus 1. If we move up to here, we have this one is equal to the overpass times the one on the right times the overpass to the minus 1. And that's that rule. And here we have this one, the one on the left as you go around, is equal to the overpass times the one on the right times the overpass to the minus 1. So that's that rule. Now let's do some actual algebra with these. We start off with this, x is y, z, y to the minus 1. Now we substitute for z from there, and that gives us x is y, x, y, x to the minus 1, y to the minus 1. Now let's multiply on the right by y to the minus 1. So on the left we get xy and y, x, y, x to the minus 1 because the y to the minus 1 times y has cancelled out. Now we do this several times more. First of all we multiply on the right by x, and that gives us x, y, x. Then we multiply on the right by y to the minus 1 to cancel out that. That gives us a y to the minus 1. So we then multiply on the right by x to the minus 1. That gives us that one and cancels out that. Then we multiply on the right by y to the minus 1. That gives us that, cancels out that. And what we get is this very strange rule, x, y, x, y to the minus 1, x to the minus 1, y to the minus 1 is equal to 1. Now we've worked that with the trefoil. Now we're going to harder work. Let's do the same thing but with this one, the pentoil. So we label the overpasses x, y, z, w, and v. Now I'll just go over to some of the few of these rules just to illustrate how they come. Here we have the one on the left is the overpass times the one on the right times the overpass to the minus 1. And so on, we go through all of these other crossings, and we get these 5 rules here. Now, if you do quite a complicated bit of algebra, what you land up with is the following rule. X, y, x, y, x, y to the minus 1, x to the minus 1, y to the minus 1, x to the minus 1, y to the minus 1. And that is going to be equal to 1. Now, this picture shows what it actually means. You go round with your loop around x, round y, round x, round y, and round x again. Then we go under y, under x, under y, under x, under y, and back again. So this particular formula is represented by that particular path going round our knot. Right, now let's do that again with our real knot and a real piece of string. So remember that here we have the formula. Now this is what we do. We do x, y, x, y, x. Now y to the minus 1, that means go around the other way. Y to the minus 1, x to the minus 1, y to the minus 1, x to the minus 1, y to the minus 1. Then we tie the ends together. And here we have our string really tied on the knot. Or do we? Well, let's fiddle around. All this up here and this up here. That goes round there, and this goes round here. This goes round here. And away it comes. So the formula really does work. Right, the next question is, where does all this lead? Well, there are two possible answers to this question. First answer is that following questions, wherever they may lead, involves discovery and understanding, and this is basic to human thought. The ultimate applications are not easy to think out or to foresee. Thus, the present trend, which argues for immediate exploitability, is in fact a danger of drying up the wellsprings of inspiration and innovation. But there is a second fact, which is that these ideas have already led to new ideas and new discoveries and new applications. The idea of knots and knotting is important in the theory of polymers and in the applications of polymers, those long strands of molecules which are very important in the plastics industry. Secondly, and here we come to another slide, here are some diagrams of motions of three separate particles which come from equations which describe the weather. Now, if you follow these out into particular bits, you see that one of them is a knotted path. It's a particular kind of knot called a torus knot. Another bit is a trefoil, our old friend the trefoil. And the third one is an even more complicated knot called a type -3, -7, 2 pretzel knot. Now, the most recent application is to one of the basic building blocks of life, the DNA molecule, and its replication. So here's a slide of some DNA taken by the American biologist Nicholas Cozzarelli. At the top you see the electron microscope of the DNA. At the bottom you see a line drawing of it. And what you see is you've got two molecules of DNA, and they're both linked, and not only that, but one of them is actually knotted. And in replicating, DNA has to unknot itself before it can actually replicate itself. Thus we see that the idea of knotting is and unknotting is one of the basic aspects of life. But let's round this off with a quotation from our old friend Ashley, the great author of this famous book of knots. Throughout history, the thrill incident to the pursuit of untrodden ways and the joy that attends occasional discovery have ever been accounted sufficient rewards in themselves for almost every human effort and sacrifice. And that's also a good motto for mathematics. Thank you very much.